Okay, so this is question 1C from last night's homework. It's about a cardinal who flies 22 meters east, lands on a post. That 22 meters is covered in 2.9 seconds, and then willy-nilly decides to go 11 meters north in 1.5 seconds. I've broken out the givens over here, and I like to see that on your problems. I like to see the givens broken out and the requireds. And so the two givens were displacements, 22 meters east, 11 meters north. These are both vector quantities, and this is time, so this is a scalar quantity, 2.9 seconds and 1.5 seconds. And our required is to find average velocity. And average velocity is a vector quantity. Now, when we go to add these two things, because they're vectors, we can't just add 22 to 11. They have a direction and they have a magnitude. And so we can do this just graphically by drawing them out. We can also use trigonometry. And fortunately with this one, we can actually use the Pythagorean theorem. Okay, I'm trying to make them to scale. There's 22 meters to the east. Here's 11 meters to the north. Cute little cardinal. Okay, we've added them tip to tail the way you're supposed to do with vectors. Fortunately, east and north are perpendicular, and so this is going to turn out to be a right angle triangle. So there we go. We have a nice right angle there. And this is our resultant vector. This is the average displacement right here. And because it's a right angle triangle, we can just do 22 squared plus 11 squared to find that. We also have to find a direction because this is a vector quantity. And so we have to find the theta here. We can find theta any way that we like, but I am going to use arctan of 11 over 22, which of course is just 1/2. And where's arctan? So arctan 0.5 is 26 degrees, 27 if I round. And so theta is 27 degrees. So there's my direction. And my displacement here is actually just 22. The square root of 605. And so that is 24.59, and so because this is two significant digits, this is 25 meters. And so we would say the average velocity of this cardinal is 25 meters. And we'd have to divide that by the time, which is 4.4 seconds. And we would say that is 27 degrees. No, we would actually say east, 27 degrees north. Okay. And so 25 divided by 4.4. I'm going to use 24.5 divided by, wait a minute. Yeah, 4.4. Okay, so 5.6 meters per second, 27 degrees north of east. That is our final average velocity for that cardinal. Now, the second set of questions that were a little bit disconcerting, mostly because they are unrealistically produced. They imply accelerations that can't possibly exist. Nonetheless, good mental exercise. And so this is what you would find for question 2 for the practice exercises, where we're given these displacement time graphs or position time graphs. And we're being asked to figure out what the velocity time graphs would look like. And so willy-nilly, there we go. Displacement is increasing. It's not increasing as much. Displacement is decreasing, and we're being asked to find out what velocity looks like. And so notice this divides nicely up into 3 zones. And so velocity is just the slope of the displacement time graph. And so if I look through here, this is actually a constant velocity. Displacement is increasing at a constant rate. The slope doesn't change in here. So I'm just going to put a nice straight line for the first zone. There we go. Here's the second velocity. Notice the slope is a little bit less. And so there's a sudden velocity change. I don't know, it's half, something like that. So now we're on to our third zone. The slope has actually gone negative, so we have a negative velocity way down here. And that is actually what the velocity time graph is supposed to look like. You never get a change in velocity like that in real life, and so that's why it's sort of a bit disturbing to go from this to this. But that is how you do question 2. All right, let me know if you need more help or more examples for the homework, and I'll see if I can fit them in.